Okay, should we give them a minute? I guess we can just get started. So today we're just kind of going to continue on with where we left off the last week and like maybe make some of the plots a little bit nicer looking and decide how we want to present some things, and we'll learn some new concepts along the way. Since Maddie wasn't here last week, I just want to kind of go over this problem. The reference paper is listed, but this is the basic issue of we have some data and we believe that those data kind of vary in some kind of a linear relationship like this. In this case, the y-axis is the amount of drug left in the blood over time. I think in this paper it was between, it's this anti-anxiety medication called lorazepam, whoops. And I think they measured between like, oh my God, where's my mouse? There we go. Between like 1 and 48 hours, something like that, I can't remember. And we want to have some kind of relationship that we fit between the decay of the substance in the blood over time. And then they also did this in 2 different populations with different genotypes, and they found some sort of a relationship. So maybe this case here, we have an interaction between the drug time relationship and the genotype. So this increase is a change in the intercept, right? So we're just starting at a different level already. So the genotype number 2 already has a higher level in their blood. Of course, you could think about in the paper, did they control for that really well? Like maybe the people didn't take exactly the same, I mean, who knows why? There might be a lot of reasons why the starting level in the blood is different between 2 groups that might not be due to the genotype. But what might change due to the genotype is the slope of this line too, and that's an interaction. So we talked about last week how interactions work. Like you could just have something where just the intercept is changed, where the time relationship is basically the same, but a group 1 and group 2 start at a different level, right? And you could have a situation where you have an interaction where maybe they start at the same place, but they have a completely different slope. And you could have both things happening. You could start at like a higher place, but also change the slope. So all of these things are possible. And in this case, this is sort of, we see both of these things happening. And we talked a little bit about how we model that mathematically, where what we do is we say some general equation, y is a function of b0 plus, let's say, b1 x1 plus b2 x2 plus b3 x1 times x2, and how this changes the, hey, what's up, Christian? Check the Slack for that new code that I just dropped in there. Maybe you saw that before. It's basically the same stuff that we just ran last week, but it just kind of gets us to the point where we want to be now. I'm just going to going over stuff for Matt who wasn't here. So let's pretend that x1 is how we code the group. So this equals 0 if group number 1 and equals 1 if group number 2, right? And then x2, let's say x2 equals time, right? So this is a slope. This is a change in the intercept. And then this is a change in the slope. So how does that work? If we had an equation for just y of group number 1, right? In group number 1, x1 equals 0. So then what do we have? We have b0 plus b2 x2, because this thing drops out of the equation, and so does this thing, because those are both just 0. And then if we have, why can't I see? If we have y of group 2, then we have b0 plus b1, right? And this is the new intercept, right? Plus b2 plus b3 times x2, right, which is the new slope. So b3 represents how the slope is changing. So, sorry, I can't see. The lighting glare situation in here is such that I can't see. Oh, there it is. So this is a change in the slope that's due to being group 2, and then this is a change in the intercept. So you can see how that is. If we're group 2, then x1 equals 1, and then this thing equals 1, so then b1 stays in there, right? And so then this is just, this is saying what situation, right? This is saying exactly this, where we have y of 1 and y of 2, where we have a line that is based on this equation up here. And then we have this other line that starts at b0 plus b1. Now remember, b1 could be positive or negative. So b1 could be negative, so you push it down instead. But b0 plus b1, so this increase, you're going to start up here somewhere. And then b2 plus b3, well, if b3 equals 0, then they have the same slope, right? If it ends up that being the case, then that's the same slope. But if b3 is positive, then the slope is steeper in a positive way. Or maybe if it's like negative slope like this, it's bringing it closer to 0, or maybe the other direction. Or if b3 is negative, then you maybe make it less flat, or you change the direction of the thing. So if b3 is significantly different from 0 after the fit, then you're going to have some change to the slope. And so that is able to encode all this. And so in one equation, we can encode something via this x1 variable. We can encode a group, which is not a number, it's a category. But the way we encode that is by saying you get 0 or 1, depending on if you are group A, or 1 if you're group B. And so that's how you get to encode that mathematically. So that's what we did the other day. I'm going to go back to here, and I'm going to go ahead and start to run some of this. And what I'd like to do is kind of go over, so that's the basic idea, right? We've fit this model. And if you look down here, if you run the code and then you just type MDL after you do that from the command line, you can observe what the model looks like. So you can see in the model that you have the basic intercept. This is the same thing as B0, 1.4 or something. Then you have this B1, which is how the intercept changes when you're the other group, right? So if you're genotype G22, if that equals 1, right, if you are that group, then we're going to add this value to this, and that's the new intercept, right? And then time, this is the basic slope over time, so we're negative 0.02 drug units per time. And then G22 times time, this is the interaction term, this is what we add to the slope if we're the other group. Right? So that's how that works. So those are all four of those coefficients for that equation. So that's cool. So now what I want to ask is, if you were going to write a paper, and this is sort of what I want to go, this is like the practical part of this for today. If you're going to write a paper, what do you want to put in the paper? You just did all of this. What do you want to tell the audience in terms of like maybe a table summary of numbers? And forget about like, oh, p-values, this or that. Just like if you were like reading the paper, what would you want to know based upon their original hypothesis? And then what kind of figure would you want to see? Okay. Okay. And then what else?
The amount of the drug at certain times.
Maybe. Sure. This is a relationship with time, right? So that's encapsulated in which number? The slope. So you might want to just tell the people what the slope is, right? You might want to say, if you're group A, then we expect that you're minus point whatever units per hour. And if you're group B, then we expect you're a different number of units per hour. That might be something you want to tell the audience. So remember, this coefficient is not the slope for the other group. This is how much you change the slope by for the other group, right? So we have to physically add those. Now I can do that just by adding two numbers together, just with a calculator, but it might be more efficient to find a good way to extract this from the model and just have it spit it out, right, into like a table, right? So we might want that. Additionally, what might we want to know about for the slope, for example? A slope can be 0, meaning there's no relationship. A slope can be positive or it can be negative, right? What is a hypothesis test that I would want to report to just the basic, if you think about it this way, there's either a relationship with time or there's not a relationship with time, right? So what do I want to tell the audience about the slope?
No hypothesis is that it's 0.
Right. So I return some p-value that is, we have a relationship with time. So not only is the slope negative 0.03, but that is significantly different from 0, meaning, yes, that fitted this. So to do that, we have to calculate something called the standard error of that slope, right? And then that's used to do a test, right? So that's a calculation on whether or not this slope is significantly different from 0. Because it could be that the error means we're plus or minus and it's basically at 0, right? We're just around 0. What's up?
When you just have like two slopes, how do you determine the threshold using which you tell like whether a slope is significant?
Right. You use something called a t-test, right? And so you take the value of the slope, which if you think about a t-test, if you think about what a t-test is for two groups, it's the difference in the means. But when you generalize that what is a difference between, that's the change, right? The rate of change, which is the same thing as a slope. So if you have a standard error, which I'll show you how to calculate for that number, then the t statistic is just that rate of change divided by the standard error, right? So it's the same thing. So I'll show you how that's calculated in the model. And then you can calculate a t statistic for the slope for group A, one for the slope for group B, and then you can tell the audience whether or not that slope is significantly different from 0 in both groups, right? So that's something you can tell. You can also tell me whether or not the slope is significantly, the two slopes are significantly different from each other, right? So you can tell all these things. You can say whether or not the two slopes are detectable as distinct from one another, or whether or not they're essentially the same, right? These are all sorts of things that you can tell the audience. Additionally, you can do the same thing for this change in the intercepts, right? This change in the intercepts. Now, the main intercept, which is just the B0, we expect there to be some drug in the blood, just period at all, because they took the drug. So this is always going to be significantly different from 0 for like something, because we literally gave them a drug and they have the drug, right? So it's unsurprising that that intercept is not 0 because there's drug in them. But what might be different or not different from 0 is the change due to the other group, right? So this is essentially the same as a normal t-test. Like the change in the intercept is what a normal t-test, when you think about two groups, is doing. At that baseline, t equals 1 hour, what's the difference between the two groups? Well, that's what this is, right? That's that first number, right? So there are two things that can be changing. We can have a difference in the baseline between the two groups, and we can have a difference in the slope, and we can report those things. So we want to tell people what the slopes are, because again, if you're reading the paper and you're going on a spiral and trying to self-diagnose yourself, and you got your 23andMe results, and you found out that you're genotype B, you're like, oh no, if I take this drug, I expect from this one paper, however many people they studied, that I should expect there to be more or less drug in my system over time because I'm this genotype, right? So you might want to know that number just for your own, or to tell your doctor. I don't know. So those are useful pieces of information. Now for the plot, what kind of plot do you envision for this?
I thought it was a table.
What's up?
I thought you were talking about like this.
Sure, I'm changing gears. So now I'm asking a different question. Yes, so we talked about what we might want to put in a table. Now, when it comes to a plot, if I want to show graphic data for this, what would I want to show you?
Scatter plot with like lines fitted.
Exactly. So we want to show scatter plot, and maybe we give each group a different color. Maybe we don't have to. We could give them a different type of thing, like a circle or an X, whatever. You could do it that way, especially back in the day when you didn't have color printers or whatever. Maybe two different colors. And then you'd want the fitted lines, like the model lines for each of those. And if you want, you can also calculate a standard error for those lines. So you can create like shading around the lines to give some kind of estimate. Because this is a model, and it's a fitted model. It's not an exact thing. So you want to give some estimate of what the error around that fitted is. So we have two things. We have a table of some useful numbers for people to know, as well as a plot that shows the scatter points for the data. And there's some things that we might want to do to those scatter points to tweak them a little bit. Imagine, again, you have lots and lots of data. You might want to scooch all the data points around a little bit by a tiny amount, because if you put them all in one line, you can't really see them all very easily. So there are a few different visible things you might want to do to visual things you might want to do to the plot. So I'll show you how we do that. So the first thing is some topics in this that I want to talk about are some reports of different things you might want to do. So the very first thing that you might want to show is just what the table of the ANOVA is. And so I'm going to go over what that is again. So that's calculated up here with this line. If you already ran this line, you can just type ANOVA.table or just run that, and it'll show you what that looks like. And that's this down here. This is called an omnibus test. What that basically means is, do we even have a significant model of any kind at all? Is there something going on, or do we just throw all this data away because we can't make any heads or tails of it, right? So that's just telling us a general model statistics. Typically in papers, you will report this information, whether or not dividing your data into two groups at all, which is this factor here, does anything to the model, i.e. does it improve your model to separate into group A and group B? Is there a significant effect of genotype on the data, right? Is there a significant effect of time on the data? In other words, can we even detect, regardless of what group you are in, can we see any kind of time relationship, right? Is that even there at all? And then, is there a genotype by time interaction? What that means is, does the slope change? Do we have a significant detection of whether or not the slope changes? These are not telling you anything specific other than we have some effects in the data, right? So it's a very sort of thing. The general rule in linear modeling statistics is that we do a test like this up front because, as we know, there's something called the type 1, type 2 error, right? So the more and more tests and hypothesis tests and p-values you calculate, the higher chance that you have a false positive result just by chance alone, right? So it's nice to have a summary statistic that just tells you, OK, there's significant relationships in the data at all before you start calculating a million little t-tests and doing a lot of things. It helps to control the type 1 error and control the false positive rate. Because you might go in and just start extracting every possible combination of slope and comparison of this or that and conclude, aha, I've just run 20 tests and I found a significant result. Whereas what you should have done is run this first and avoided the type 1 error by just determining that at a broad level, we didn't really detect any interesting effects in the data at all. So to show you how this is calculated really quickly, to show you how you can export this, that's the first thing I wanted to show you. There are a couple different ways that you can export it, OK? The first function I can show you for export just makes a text file. This is the capture output function. So the capture output function, I'll just type it from scratch up here. The capture output function just takes the output to the console. So in this case, capture.output, I'm going to feed it the ANOVA.table. And I'm going to say the file is, I'm just going to call it ANOVA table.txt. So that's just the file name. And when you run that, all that does is it creates this little text file in here. And this isn't anything particularly nice. Like you can't really open it in Excel or anything. But it just is dumping the summary of what you can see at the command line. So you can imagine if you have a script that is running a bunch of analyses, you can just do this. It takes the text form of whatever's on the console and just dumps it to a file. So that's useful because then you have all of this stuff and you can add this to your Word document or your report or whatever. And then there you have it. This is exactly what it's at. But you couldn't really easily open this in MS Excel. Why? Because there's like a different number of spaces. It's not easily delimited. It's like you can't easily pull that into Excel or another piece of software like that. Notice R does this by default just for visualization. The precision estimate is like double epsilon or whatever for R is usually considered to be, I think on 32-bit or 64-bit machines, something like that, is 2.2-ish times 10 to the minus 16th. Basically, R thinks that anything below this is effectively 0. Right? And so if it is any value, this value or below, in a report like this, even if it can be calculated exactly, like with some more precision, R will report less than 2.2 times 10 to the minus 16th. Okay? But if we convert this to another type of data structure within R, it'll report the exact value it calculates. Occasionally, that value might be exactly 0. And that's totally fine. You can have p-values of exactly 0. How is that possible? P-values are calculated from integrals. And so it is possible sometimes that the area under a curve, if you're like that far out somewhere on the curve, can be essentially equal to 0. It can be like so far to like negative infinity or whatever that the limit that it approaches that is effectively 0. And that happens sometimes when you have millions of data points and there's a massive effect. Like you can imagine if there's like a twofold effect between data and you have like 100,000 data points in each group, that integral of that statistic or whatever, that end of the curve, which we can talk about how p-values are calculated down the road, that could be essentially 0, right? There could essentially be so far out in the distribution that there's nothing out there. The area under the curve is 0. So it can be 0. It can be something in between. So if you want to make this more accessible to something like MS Excel, you first need to convert it. So I use this as data frame thing. Basically, that's going to take the summary report from this table and make it into a data frame. Frame meaning like a normal matrixy like thing that has columns and rows and whatever, because then that you can directly export correctly as like a CSV or an Excel table, which the other thing you can't do. I might in real life overwrite the old thing and just leave it as the same variable, but for this purposes, I'm just going to do that. It looks basically the same, but you can see there's none of the extra markup stuff, like all these asterisks and all these things that are marking up this text. It's just a table. Right? So now that this is just a table, you can see that that value is 2.3 times 10 to the minus 48th. right? So it calculated some value. Obviously, it thinks that the effect of time is the most significantly detectable in the data is the fact that there's time, and then there are other effects in the data as well, but that's like the strongest thing, which we'll talk about that strength in a second. But then this, you can directly export. You can see like residuals, which is the remaining, after you fit the model, what are the residuals? That's the observed minus predicted values, right? So how much, what's the variance in that? It has to fill in some things for these columns to make it a table, because tables can't have any missing data points, right? So it fills in NAs. R uses that like NANs in MATLAB for MATLAB people. So then you can use this write CSV function, and then you can just write CSV ANOVA table, which is the data point. Oh, what's up?
Why did you grade that like ANOVA table to on line 26?
Right, I could have just made it this, but then it overwrites the old variable. So I'm trying to be good coding practice and not overwrite an old variable for no reason.
Then why are you still writing ANOVA table?
Because I made a mistake. Oh. So right, because this is what we call a mistake. But you know what's funny?
You should be trying to write down the data frame instead of.
Yes, correct. So that's a mistake, and thank you so much.
I thought
Yeah.
the right CSV.
Thank you for correcting me.
So much.
No, Irene correctly correct me. So yeah, no, you're right. That would make no sense. So first you convert it to this. But it's interesting that you point that out. I wonder if R is smart and just converts it to a data frame under the hood without me having to do that. So let's test and find out. Because I think I did this with that by accident. And maybe that step is not unnecessary. So maybe it automatically does it. You see, it doesn't give me any error. And then let's look and see. If that's the case, then the write CSV function is actually smart. Yeah, it did it. Okay, so never mind. So just kidding. Apparently, you don't need to do this step at all. So you can just use the write CSV function. I didn't know that. I thought you had to convert it to a proper data frame first. So apparently, the write CSV function is smart enough to know that if it isn't in the proper format, we're going to force it to be the proper format and then write it out. So yeah, so you can just use write CSV. So never mind. Just kidding. What's up? Yeah. Why don't you do that real quick? My timer went off because I need to check my eBay auction. Hold on one second. So I bid on a new phone case, and I don't want to lose the auction. So you don't know what an eBay auction is? Hold on one second. Hold on. I'm winning in 37 seconds, you guys. Well, because this phone case is normally $64. So now in the recording, when this goes onto the YouTube, they'll see this. But I just want to know. But I need to not lose it because I don't want to have to pay more, and I want to make sure I don't get outbid. Well, right. So I had to get a new phone because I broke my phone.
It's very pricey though.
Yeah, they're more expensive. So I found a used one, or not a used one, but a lightly used one for $20 instead. So this is good. Maddie had to go do that. Did I win? Did I win? I'm gonna win. I'm gonna win. I'm gonna win. Okay, great. I won, I think. We're determining the winner. No. I obviously won. What do you mean you're determining the winner? Well, I think I won. It would have told me that I got outbid, so I'm going to say that we don't need to do that anymore. Great. Okay, so back to the lesson. I'm not going to edit this, by the way, because I don't have time to edit this video, so that's just going to go in there because I don't have time to do all of that. So I want to talk about a little bit about how the stuff in the ANOVA is calculated and what the terms mean before we continue. So if we just kind of go back, oh my God, why is my doctor calling me right now? Why is so much happening? So I'm going to go. I'm going to go back here. I just want to talk about a little bit about this and each of these things in here. Okay, so how do we arrive at each of these things? Just briefly, I want to give you guys some intuition at what these numbers mean and what we can use them to compute. So I'm going to start backwards. The sum of squares, again, in general, what that means is the sum of squared differences between the observed values and the predicted values, right? So that's what we call the variance or the error term in the model. That's how good did we do. And so the more predictors we add, again, you might be able to overfit at some point, but if you add predictors that are useful predictors, that number should become smaller, right? Because if the observed values and the predicted values are very close, then there isn't much left. right? Because if you're able to perfectly predict every single data point, there's no error, right? We know that's never going to really happen in real life, so that number gets smaller and smaller. So this is just the observed values minus the predicted values. So each of these terms, okay, which this is how the p-values for these terms are computed. This sum of squares represents the difference between, and this is true for all ANOVA, even the classical ANOVA, like stuff Irene was talking about, where she was confused about this from the way she learned this maybe in the past. Even in classical ANOVA, the sum of squares term refers to the change in the error, so the change in the observed minus predicted, that happens when you add a new predictor to the model, right? So if you consider, for example, the time interaction, this term here is 2.606, right? What does that mean? That means we have a model that fits the whole thing with the interaction, like the changing slope model, and we compare what the observed minus predicted values are from that model to a model that doesn't do that. Right? So a model that does not allow the slope to change, right? So you can do this along with me if you want, but I just kind of want to show you that these are the things, and I'll send this code out at the end. So if I had a model that had no interaction term, that's what this is right here. So if I fit the same model and I just did Geno, you can see Geno plus t, but without this asterisk sign, that's a model that doesn't have an interaction term at all in it. So just to show you what that looks like, this is a model that just has a change in the intercept, but no, whoops, model, no interaction. You can see there are only 3 terms in this model. This model has an intercept, it has a change in the intercept due to the other genotype, and it just has one slope. So regardless, your time relationship is the same, right? And then if I do the sum of squares of this is the observed values, and then this is the predicted values. To get the predicted values, by the way, all you have to do is run predict on the model, and it calculates what the predicted values are for each of those things. So if I run the sum of squares for that model, that's some number, right? So if you look at this, that is 189.4962, right? So you can see where this number is coming from. So if I go up here, you can see how the final observed minus predicted error term is 186. So this number is a little bit larger than that, because what am I not including? I'm not including that interaction term. So if I then go back and I include the interaction term, now let's compare these together. So model no interaction looks like this, and model interaction looks like this, right? So the only difference between these two models is that this model says the slope, there's just one slope. So regardless, we're just bumping you or whatever, but the slope is going to stay the same. This model says, OK, we're going to have the slope, but we're going to allow the slope to change depending on which group you are, right? So if we compare observed minus predicted from this one and observed minus predicted from this one, if there's a significant effect of this term, this 4th term, then that means that this model should result in smaller error, and that should be significantly different, right? So then that's what that term is. So if you look at both of those things, which is this SSE interaction term, whatever, if you take that no interaction minus that interaction term, you come up with exactly this 2.60603 number, which is the number that is in the ANOVA table. So you can see that right there, 2.606. 2.606 is just the difference between the error in not having an interaction term and the error in having an interaction term, whether or not you include that. This, by the way, is also used for predictive models when you want to do something called model selection. Model selection means when you have a bunch of things you think might affect the outcome, and you include them in your model, but you're not sure which ones impact the outcome or not. You can do a test like this to determine which of those are significant predictors in the model, and then remove the ones that aren't significant predictors. So if we didn't have a significant interaction, that suggests we should go back and use the model that doesn't even include that term at all to get the best prediction, right? So in model selection, which is used in lots of machine learning stuff too, which is a little bit different. This is regression learning, but you can still do regression learning. It's a simple kind of machine learning, right? This is linear regression is machine learning. Like, it is basically you're fitting a model to data, and then you might use that model to predict new results, right? So if you have a term in that model that doesn't seem to impact the error at all, it doesn't make it smaller, it doesn't do anything, you might consider for your machine learning, your AI, or whatever your utility is getting rid of that term, right? Because that term is superfluous and doesn't impact it. The slope is apparently not changing, so we just leave the slope alone. So that's how you arrive at this. And you can go back and do the similar things for the factor of time and all that stuff. So for example, in this case, how do we determine this factor of time? This is, you look at progressively smaller models. So I can do a model that doesn't have time, right? So this model only considers the change in the groups, but doesn't consider any relationship in time. And then I can have a model that includes the time, and then compare them, right? If I do that, this SS time should be exactly what is in the ANOVA table, this number 69.01, whatever, right? And lastly, you can do the same thing with the genotype. You can say, I'm going to consider a model that only has a time relationship, but no change in the intercept at all, and compare that to a relationship that has the change in the intercept, right? And then compare those two together, and then you end up with this number that is, whoops, this number, which is 10.3030. And again, that is how, in the ANOVA table, that's what these is. So this sum of squares term is, again, the change in the error, the observed minus predicted values, that occurs whether or not this particular predictor is removed from the model or included in the model. OK? So if we said, OK, we're only going to consider a time relationship, but we're not going to consider the genotype at all, or not even care about it, this is how much of a boost you get in model predictive quality. You can see all three of these terms are significant. Okay, meaning that the f-test for those terms, which we'll talk about how f-tests are calculated maybe another time, but the f-test for those terms, that comes from something called an f-distribution, you can look it up online, is based upon this sum of squares term in relation to the remaining error, right? So what's basically, it's kind of like saying what's the ratio between this thing and the error that's remaining, and like how much are you boosting the model? Like really, like how much are you improving the model by including that term? And includes to some degree how many data points you have. You have, I think there are 684 some odd data points in this data set. Cool, great. So there are a couple other things that we might want to include. One is called the R squared. We talked about the R squared a little bit before. That's the percentage variance explained. What that means is how much variance in the data is being effectively predicted by this model, right? How much of that is being predicted. That is this fourth term, 186, divided by the total down this column. So if I do that calculation, you find out that R squared is 0.30. So that means 30% of the variance in these data, and these are simulated data, is explained by this model that fits genotype and time. Now, if you think about it, that's not a very highly predictive model, right? That's actually a medium to low effect, right? That's not a huge effect. That means there's a lot, when you plotted these data, right, an R squared of 0.99 would mean that every single data point is predicted exactly where it's supposed to be. R squared of 30% means that there's still a huge spread in the data that's not being predicted by the model. And that's OK. Actually, very often, it depends on whether or not you're using a model for prediction or hypothesis testing. In this case, there's a significant effect of these groups and a relationship over time. We're not necessarily using this to try to predict brand new data we've never seen before. Like if I just got a blood sample from Irene and I knew her genotype and like I had all the data over time, this might not be very good. We'd have to test to see how good this is at predicting what her values are over time. So only a 30% R squared, maybe not so good. But for the purposes of simply hypothesis testing detection on the data we already have, we can detect significant effects in the data. And we can report that this model predicts about 30% of the variance in the data. OK? And lastly, I'm going to go ahead and add this final column in here. This is called partial variance explained or percent variance explained of each term. That's a better way than just the p-value itself at like ranking the terms at like which is the strongest effect in the data. All that is this column, each of these numbers divided by the total down the column, right? Because the total, by the way, this total sum of squares column, that is equal to just the variance in all of the data, meaning all the differences between the data points and just the mean of everything. So if you add that whole column down the middle, if I did sum of log 10 of d LPAM minus the mean of log 10 of d LPAM squared, that would be 268.805, which hopefully is the sum down this column. OK? So That's what that is. So if you take each of these terms and divide it by the total, you get a partial variance explained term for each of those things, right? And that enables you to give a sense of like effect size, what we call effect size. Effect size is like how much of effect is each of those things having. So if I add that term in, you can see that the strongest effect in the data, which is correlated to the time, or to the p-value rather, is this time relationship. So even though there is a change in the levels with each genotype, really the strongest effect in the data is the fact that in both groups there's a decaying relationship over time. And this, in English, if you were to read this out loud, this would say that 26% of the variance in the data is explained by the time relationship, right? 3.8%, which is not a lot, is explained by the difference in the groups. And an even smaller percent, about 1% of the variance in the data is explained by allowing one of the groups to have a different slope. So really the strongest effect is this time effect. And then 69.5, that's saying 69.5% of the variance in the data is unexplained. Whoops. So that's what we would say. So you want to, if you said that all in English, that means actually we're not explaining a lot of what's going on. There might be a lot of individual to individual, like somebody, maybe everybody's taking their blood draw at different times during the day, and that's affecting it, right? So maybe if you had other information about their age and their weight and like a million other things, maybe those other things would do better prediction. And if you had information like their age and their weight and their blood type and like a million other things, and you added that into the model, maybe you would make the model better. Right, so we don't know. At some point, we have enough data in this, I think there's like 684 rows, that they could probably tolerate some more predictors that would do a better job. OK? Cool. Great. So that's the basic summary statistics. Now, I'd like to move on to calculating the individual slopes, right? Because you might want to tell us group A has this slope, group B has this slope. This stuff is pretty easy to calculate. Do I have any questions about the basic stuff? Basic fundamental tests? No? OK. I'll continue on. So switch over here. I have 4 coefficients, B0, B1, B2, and B3. And what do I know? I know that the intercept for group 1 is equal to B0. And the intercept for group 2 is equal to B0 plus B1. And the slope for group 1 is equal to B2. And the slope for group 2 is equal to B2 plus B3. Oops. Those are things that I know, right? Just from my own interpretation of the model, how we fitted it and all that stuff. How I extract this is by doing something called a linear combination. Right? So I apply a linear function to these terms. So what does that mean? Mathematically, if I just want to extract these directly, that means I consider a vector that I multiply each of these terms by to add them together that will output these specific results. Right? So what does that mean? For B0, how would I do a sum of the whole set of coefficients to acquire that answer?
1, 0, 0.
Correct. Exactly. So I would multiply that vector by 1, 0, 0, 0. And then multiply that using linear algebra by 0, 1, B1, B2, B3. And this is called a linear transformation, right? So people that do lots of imaging work, again, you can do matrix multiplication to do all sorts of rotations and summations and all these things to matrices. In this case, again, for those who haven't taken linear algebra, which I think might just be Maddie and Christian, linear matrix multiplication means you have a vector like this, and you multiply it by another vector or a matrix, and you take each term, this times this, plus this times this, plus this times this, plus this times this. Does that make sense? That's just how the operation is defined. Okay. Secondly, I can then calculate the other one. So if I wanted to do B0 plus B1, what would the vector be?
1, 0, 0.
Correct. Cool. And if I wanted to do slope of G1?
Is that B12?
Oh no, it's you're right. It should just say B. It should say B2. Correct. And if I wanted to do B2 plus B3? Correct. So this is a matrix that's a linear transformation of the betas that outputs exactly these 4 results. So using linear algebra encoding, I can create that matrix, multiply it by my coefficients, and immediately get all of the things I want to report, which is the intercept for each group and the slope for each group. Okay? So that's very convenient. And the more you learn linear algebra, the better and faster and easier your code will look and the more elegant it will look for these reasons. You can have one matrix times the vector of coefficients, you get the answers. Okay? And I'm going to do some extra things in R to show you how you make that even into a report, because in R, which is nicer than in MATLAB, a matrix can have names for the rows and the columns, which means the output vector has those names that travel with it, which is really, really handy for summary reports. MATLAB, everything is like a naked matrix, and you just have to believe that everything is right. So I'm just going to reformulate this on this because I want to show you a couple things. So we just talked about what we wanted to report. So I'm going to call this the intercept of group 1. I'm naming the rows, and this is for a reason, because we're going to use R to do this as well. The slope of group 1 and the slope of group 2, right? So we're going to have 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 1, 1. And then this, the columns, I'm going to title the names of the coefficients themselves. So B0, B1, B2, B3. And then we're going to multiply that by the vector that actually has the numbers B0, B1, B2, B3 in it. The most important thing, because computers are going to do all the matrix math for you, you're never going to have to do it yourself except maybe on a linear algebra test that one time in class, right? So you're never going to have to do this math yourself. The most important thing to remember about matrix math is the dimensions, okay? So what are the dimensions of this matrix on the left? 4 by 4. What are the matrix dimensions of this vector?
4 by 1.
Correct. So as anyone who's taken linear algebra knows, if you take a 4 by 4 matrix and you multiply that times a 4 by 1, the inner dimensions cancel and the output is a 4 by 1. Okay? So you always have to track the dimensions. The inner dimensions for matrix math to work, the inner dimensions must match each other. They must be identical. Okay? And why is that? Well, it's because in order for this to work, we have to have one value to corresponds to each of the coefficients. In this case, this is along this dimension, and then this is along this dimension, right? So if you don't have exactly 4 to match, then you can't do this operation, right? So these dimensions match. So we have a 4 by 4 times a, times a 4 by 1 is going to equal another 4 by 1 with those specific computations that's going to return intercept for 1, intercept for 2, slope for 1, slope. I don't know why I dropped the E off, but it's fine. Slope for 2. OK? Great. Cool. So this is relatively straightforward and easy to do. So in R, let's go ahead and calculate this. So I'm going to call this matrix W. That's for reasons. In linear algebra, especially in statistical linear algebra, linear transformations are often labeled with the letter W. I don't know why. OK, cool. So W is going to equal, now how am I going to assemble this matrix? The easiest way to do this is using the rbind function. That means we're going to take a bunch of row vectors and stack them on top of each other, right? So to do that, we're going to do rbind. And I'm actually going to put in an enter here because R does not interpret carriage returns, so you can add as many as you want for clarity. And I'm going to use the C for the vectors, and we're going to have 1, 0, 0, 0. Whoops. And then we're going to have C 1, 1, 0, 0. And then we're going to have C 0, 0, 1, 0. And C 0, 0, 1, 1. OK? So then W should look like this when you're done. And while you guys mess with that and get it right, I'm going to go ahead and add some things to this. And I'm going to say that the row names, this is where this fun part comes in for W, equals intercept 1. I'll just make it lowercase. Int 2, slope 1, slope 2. And then I'm going to say that the call names of W are equal to the names of coef model. the W looks like this. Okay, so I'm going to go over these couple things. Did everyone make the main matrix part work already? Everybody got that? Christian? You got that? Right, sweet. So we're going to assign the names, and I'll show you why we assign the names, because they propagate through all the calculations. So in R, even a vector, each element can have a name, a title, right? So I'm going to assign row names. So row names for matrices, you have 2 dimensions you can give a name, row names and col names. For vectors, you just have the word names. So coef model pulls the coefficients, okay? And it has the names associated, so I can just pull the names. So that's why I did it this way. Names does this. And so each of these can assign those properties. And so you end up, everyone should end up with a matrix that looks like this, where each of the names, now they're not named B0, B1, B2, B3 like I did when I was doing my toy example. They're named however linear the LM function wanted to name them. But you should have something that looks like this. Great. Then finally, that's W. Now I'm going to say, let's call it B is equal to coef model. Okay, that's just the actual coefficients themselves. So there they are. And by the way, R treats a vector as dimensionless, so it'll do the calculation correct whether or not it's a row or a column. Like, it'll do the correct things. So in MATLAB, you actually have to tell it which dimension, whether or not it's supposed to be a row or a column. You have to know whether or not it's going, and that's very annoying. But R is, you can't, so MATLAB may give you an error in matrix multiplication if your vector is meant to be a column but is actually a row. And the default in MATLAB is a row, actually. So you have to remember to use the semicolons to make it a column to transpose it, right? But in R, a vector is dimensionless, so it just does the computation correctly. So great. So now, if you wanted to calculate what that transformation was, let's call it slopes. I don't know, there are intercepts in there too, but whatever. Let's call it slopes equals W. Now, to do matrix multiplication, you have to use this funny thing, which is percent sign times percent sign B. Okay? And then, what's nice about this is that slopes has those labels associated with it. So int1, int2, slope 1, slope 2. And since it's a column, it's like nicely exportable if you just wanted to like put this into a thing, right? So this is what you might want to report to somebody and say, aha, this is the level for the one thing, this is the level for the other thing, this is the slope, and this is the other slope, right? And just to confirm that that's true, if we look at B, that last slope should be minus 0.2567 plus 0.0086 or whatever, and that's, ooh, really? Oh, yeah, because I forgot 0. I was like, what? There we go. OK, so 0.2670086 equals 0.17, so that's this number right here. OK, so that's how you can easily compute that without having to do those calculations. You just have to design this little W matrix to do that. OK, so now the next thing you might want to know is what are the standard errors associated with each of these numbers, right? Because when you look at the model, so I'm going to go to, if you ran this code up above that I included in the things that I sent everybody, you have this summary table, this summary model thingy. That does a t-test for you, actually. OK, but it doesn't do the t-test on those quantities. It does the t-test on the betas, on the coefficients. So it's saying whether or not each of those coefficients is significantly different from 0, B0, B1, B2, B3. That's not what we actually want to report. We want to actually know the literal value of the slope. What's the standard error on that number, which is a combination of 2 different betas. So like, for example, the slope for group number 2 is this number plus this number, right? So that's going to have its own standard error that's different from either of these standard errors. So does anyone remember, maybe from chemistry, analytical chemistry, or some other math classes you maybe have taken, propagation of errors? Like if you have 2 quantities and you add them together, how do you calculate the standard error of the resulting quantity? Who can tell me?
It's like the L2 norm of,
Sure. Which, just say that in regular arithmetic speech.
Pythagorean theorem of the magnitude.
So the square root of the sum of the squares, right? Yeah, exactly.
Of the partial derivative.
Exactly. Sure. Yes. But in simple terms, for just 2 numbers that are simple numbers, yes, that is how you extrapolate it, right? And we're going to calculate it in that way using matrix algebra. But in general, just for 2 numbers, if you have number A and number B, and they each have an error associated with them, and you add A plus B, what's the error in C? right? That's the square root of the sum of those two elements squared, right? Assuming that they don't have a covariance term or whatever, but assuming they have independent error terms. So you may remember that from basic, I feel like I did this in analytical chemistry because very often we would have homework assignments for lab classes. We'd be like, okay, we have the weight of one thing and the weight of another powder. What's the error on the balance? And now what's the error on the weight of both of those things added together or something like that? Or like I dissolved this thing in this much liquid. The measurement error on the mass of this and the volume of this was this. What's the measurement error on the dissolved? All that stuff, right? So that's annoying stuff from analytical chemistry, but it's basically this basic thing that if you have A plus or minus sigma of A and B plus or minus sigma of B, what is sigma of C in terms of those other ones, right? Because that's basically what we have to figure out, right, from these two slopes, because we're adding two numbers together. So this is, in general, the square root of sigma A squared plus sigma B squared, right? That's, in general, what sigma, that's Pythagorean theorem, exactly. Sigma C equals this, right? Great. What's up?
I do remember that I need to divide like the sigma A and sigma B squares with.
Oh, do we need to do that too?
population.
Oh, the size of the population. Yeah. If you want to normalize it, yeah, you're right. Yeah, you probably should do that. Maybe I don't remember exactly. So don't quote me on this, YouTube people. When you listen to this, I don't remember. We look it up on Wikipedia. But it is essentially, regardless of the normalizer you use, it is essentially this function. Essentially this. Right. Great. Okay, cool. Right. The square, the things. That's how you combine two standard errors together to get a new one. We're going to generalize that to matrix math. Okay, and we presume that these betas, they have something underlying that's inside the model that the model calculates from derivations of the actual, like how the model's fitted, right? From least squares regression that I'm not going to go into today. But you can easily derive yourself from a matrix of second derivatives, actually. This is called the variance covariance matrix. Okay, so I'm just going to call that V. Okay, and what is V? And we could just extract this from the model without calculating it because it's built in. V is going to be the variance covariance matrix B1, B2, B3. And it's going to have a bunch of numbers in it. OK? This is from the fit. What are each of these numbers? Can someone tell me what they think in this matrix? What are the numbers down the diagonal?
1.
No.
0.
Nope, they're a number. They're the error term associated with each of the betas. Okay, so this is going to be the sigma squared for beta 0, and the sigma squared for beta 1, and the sigma squared for beta 2, and the sigma squared for beta 3. Okay, this is a variance covariance matrix. So what are the upper and lower triangular terms? Who can tell? Maybe Josh knows. They're the covariance terms. Does anyone know what covariance means? I could just tell you real quick. It is how, if you consider what these are, right? What is beta 0? That's the main intercept column. Forget about that. Let's consider the other ones that are data columns. You might have, let's say you have age and weight, okay? You have some function, the amount of drug in the system. The amount of the drug in the system has a, maybe let's say it has a relationship that's significant with both age and weight, right? So it has a linear relationship with age, and it has a linear relationship with weight. And then maybe there's some interaction of those two things together. But what else do we know? We know that as people get older, they tend to weigh more. So there is a correlation relationship between those two terms. It's not as neat as just age and weight are two totally independent random things, right? There's also, between those two columns, a little bit of a relationship. Now, hopefully, we've acquired enough data that we've like counterbalanced that a little bit, because so imagine you took someone at ages 10, age 20, well, maybe what time are you done maybe developing in terms of your weight, unless you get a lot bigger as you get older. Maybe like age, let's consider early development when you're changing weight a lot. So age 2, 5, 10, and 20. If we took those ages between two people and also took their weights at each age, and we found there was a significant effect of age and a significant effect of weight, is that really valid to say we have two different effects? No. Why is that not valid, Josh?
Because there's only one relationship.
Correct. Because since they obviously are going to weigh more, you can't disentangle which one it is. Is it because they're just developing, they're a different stage of development, or is it because of their literal weight? Right? So how would you factor against that? Well, you'd make sure to have enough representation of like other people of the same age but different weights, right? But regardless, there's going to be some correlation structure no matter what. So a linear model can handle that. A linear model will result in a singularity and an impossibility of fit if you have two columns that are perfectly 100% correlated to each other by just a scalar. Like if you have the age and the weight and they're like almost perfectly correlated, you can't fit that. You either have to fit one or the other because they're too intermixed. It's like if you take one column in a matrix and multiply it by a single number and try to fit that as a new predictor, that's going to not be good for your model, right? It's going to artificially improve your model without actually improving the predictability, right? So it's not good for the model. But some amount of that's called multiple collinearity. Some amount of that can be tolerated because there's going to be correlationship structure, and some of that is going to be reflected in how these fitted numbers have covariing structure. So the degree to which you can actually take this whole matrix and convert it into what we call a correlation matrix to determine the actual correlation on a scale of -1 to 1. How much are they correlated to one another? But just simply to grab this, I'm going to go down here to wherever we had the W thing. Let's grab the variance covariance matrix for the model. So underneath where you pulled the slopes, I'm going to say V equals VCOV is the function, VCOV model. Okay. So let's look at V. Okay. So that looks like this. Okay. This now down the diagonal are the actual error terms associated with each beta, and then the off terms are the covariance terms associated with each beta. Okay? Cool. So the standard errors, if you go back to this model summary, this summary model thing, these standard errors right here, this is the square root of the diagonal, right? So if the diagonal is the sigma squared of each beta, like the variance associated with each beta, then the standard error of each of those terms is just the square root of that term. So if I took, I'm not going to put it in the code, but if I took just at the console, if I took the square root, and the diagonal function in R is diag of V, that's going to be, it's going to still, see what's nice about R is it retains the labels. This is exactly the standard error terms for each of those numbers. Okay? So now we get to do something very fun. We get to calculate the standard error of our linear combinations using matrix math. Okay? So this is, you'll have to take me on faith, but let's calculate it and see what's going on here. In general, the question that we're trying to ask is we have V for a certain coefficient set, right? And now we want to know what is V star for when we do a linear combination of that coefficient set. So what is this? Because that's the basic problem of our original simple two-number problem where we have A plus sigma of A, or let's say sigma squared. So we have, let's do this. We have A plus B equals C, and A is associated with sigma squared A, and B is associated with sigma squared B. So what is sigma squared C in terms of those other ones, right? And we figured that out. It's the sum of square, right, or whatever. So now that's the same question generalized to this general problem of if we take any matrix and multiply it by any vector of any length of coefficients, what does that variance structure look like for that new relationship? And it's actually very simple. It's the L2 norm, right? Which you can calculate directly as W times beta times W transpose, I think. Or is it the other way around? Let's see. It's either one or the other. Hold up. I think is it that? It might be that. What's up? What are you asking?
Show me another matrix notation.
Yeah. Oh, this is not. This is also a mistake.
The transpose is on the right.
Yeah, I think so too. But I'm going to double check. And actually, there's an easy way for us to check, which is right. It's called Googling. But additionally, where's my, there it is. V. There we go. Well, here, let's think about this. The way we can think about it is, hold on. Linear transformation, variance, covariance, linear combination. I think it's on the other side. Linear combinations of random variables. Oh, not all of this. There we go. Sure. I'm pretty sure. Well, here, I know how to figure it out. Whoa. Oh no. Okay, good. If I have W, the way you figure it out is, of course, if you match the dimensions. Yep. Great. Cool. I figured it out just by sleuthing it out. It's on, Josh was right. And that was the original way I wrote it too, so I was right initially too. Great. There we go. Okay, so it is what we call the, W can sometimes stand for weights, the matrix of weights. That's why it's the letter W. So it's W times V times W transpose. Okay. So why does this work? Well, let's consider what W looks like, right? B0, B1, B2, B3. And we have intercept 1, intercept 2, slope 1, slope 2, right? Now we're going to multiply this by this matrix. The way you can figure out the right way to do it in R is simply by the labels, right? The labels on this are B0, B1, B2, B3, B0, B1, B2, B3. We want a matrix that looks like this, but where the labels are the quantities we want on both dimensions, right? So if we multiply this by W transpose, what's W transpose? That's B0, B1, B2, B3, I1, I2, S1, S2, right? So if you do the matrix math, you have a, in this case, we've made it be a, why can't, there it is. This is a 4 by 4. This is a 4 by 4. Now this part doesn't have to be, only the inner dimensions have to match, right? This is a 4 by 4. The inner dimensions are the number of coefficients that we have, right? So if this was, if you had more quantities, like you could have 10 or whatever, it doesn't matter how many you had, these will cancel, and then these will cancel, and you end up with a 4 by 4 that is the variance covariance matrix of the terms that you want. Okay? And you can see that in the math. So if I wanted to calculate that, I'm going to call this VW. Let's call it VW. And we'll call that W, funny percent sign asterisk times V, percent sign asterisk times W. And to transpose a matrix in R, you use the T function. So in MATLAB, there's just an apostrophe. But in R, you use this T function like this. Okay? So then VW has int1, int2, slope 1, slope 2, int1, int2, slope 1, slope 2. So which numbers of these are the standard errors for those quantities? It's the square root of the diagonal. Okay? So in a variance covariance matrix, the square root of the diagonal is the standard errors associated with each of those quantities. So if I wanted to have SEW, okay, that's just the square root of the diag of VW. Okay? So these are the standard errors associated. Now int1 is the same. Now this is an internal consistency check, right? The standard error of int1 and slope 1 shouldn't change from the original betas because those are literally just those quantities already. Again, we're just repeating them, right? Because it's 1, 0, 0, 0 or 0, 0, 1, 0. So you can see that's 0.344, 0.1, whatever. But the other two will have new numbers, right? So the value for intercept number 2 is 0.039. That's a little different than this beta value, whatever, slope 1 and slope 2, right? So now, if I wanted to report something, I could say let's call it the slope report, is a data.frame where we call this in R speak usually the estimate. That's equal to slopes. And then the standard error is equal to SEW. And you can see that because we've named these rows and columns, these propagate as the names of the rows the whole time, which is really nice for presentation, right? So now we can tell you, okay, the value of the intercept here is 1.4 with a standard error of 0.034. The value of intercept number 2 is 1.6, standard whatever. And then the value of this slope is 0.025 and 0.017 with these associated standard errors. Okay? Cool. So that's how you report that stuff. So then you could write this to a CSV file too, and then you could just have it, and you can put that in a report. You can also do a t-test for each of these things, okay? Now, it's going to be a no-brainer that the intercepts, because of how large they are, and you can see how small the standard error is, obviously those are significantly different from 0. It's not really that interesting to tell me that there's an amount of drug in blood at time 0. We know that there's drug in blood, but the slopes are interesting to report whether or not they're significantly different from 0, right? How is this different, by the way? This interaction term up here, we can see that this interaction term is significantly different from 0. That is the amount of that B3 number, but that doesn't tell us when I add that number to, so I might want to tell you, for example, when I change the slope, do I change the slope such that the new slope has no relationship, right? This t-test is telling me that the change is significant, but it doesn't tell me how to interpret how it's changed the slope. You know what I'm saying? Does that make sense? So it's like saying this number, okay, we're going to add this number to it, and that's a real number to add to it, but it doesn't tell me after I've added that number, do I now have no slope? Do I have it be significantly positive slope? Do I have it be significantly negative? So like what's going on with that slope, right? So to do that, you calculate the t-statistic. So I'm going to go ahead and just add that to the slope report. Slope report, report, I can't spell. Let's call it t. That's simply equal to the estimate divided by the standard error. Slope report SE, excuse me, slope report $ estimate divided by slope report SE, okay? Okay, so this is the t statistic that is associated with each of those numbers, okay? And you can calculate the p-value associated with that. The two-tailed p-value, oh boy. I'm just going to take it on faith that we're going to do it this way for now, and then in the future I'll explain what this is. But it's 2 times the pt function, where q equals slope report, that t column, that's the t statistic. And then the degrees of freedom is equal to the model degrees of freedom. I'll explain the degrees of freedom concept, I think, in the future. mmodel.df residual is this thing. It's inside the model thing. And then lower tail equals false. I'll put this in the code, but for right now, you'll just have to take that on faith, and I'll explain all those concepts down the road. Oops, I shouldn't label this the same. Let's call this p-val. Okay, great. So those are the p-values associated with each of those. Did I do something wrong? Oops, I need to take the absolute value of the t statistic. Just kidding. There we go. Okay. Cool. Great. So down the road, we'll explore the topic of t-statistics. For right now, this is just how you get the p-value for those t-statistics. We'll sort of talk about what the t-distribution is. A t-distribution can have numbers on either end of the distribution, so I have to take the absolute value of that end of the distribution. Because if I just let it be negative and I'm taking the other tail, then it might be the other area under the curve. Does that make sense? So anyone who's taken the calculus of this, they kind of understand that. To get the two-tailed p-value, this is probably better for its own whole section. So I apologize if that's confusing. But the t statistic exists in a distribution, and you're trying to ask, is my value unlikely to be due to chance, right, out of this probability distribution? Well, That's the area under the curve from that value onward, right? So if that value is negative, I need to calculate this area under the curve. And if that value is, positive, I need to calculate this area under the curve. So I need to take the absolute value because that area under the curve is symmetrical regardless of which side you look on. So if I tell you to take the upper tail, meaning if I tell you to take this area, but I didn't take the absolute value, and I have a positive number or a negative number, it's either going to take this area or it's going to take all of this area, right? So taking the absolute value solves that problem. That's why I do that. I'll explain that, I think, down the road in another thing, but that's how you calculate that. And so then you have that. So both of these slopes are significantly different from 0. The intercepts, again, the p-values are very large because the errors are so small. But importantly, the two slopes are significantly different from 0, and you could export this to a slope report and say, aha, here are the slopes. OK, great. Cool. So again, the main thing to take home here is this. If you need the standard errors associated with any linear combination of the things, this is how you do that. You have to have this weights matrix. OK, so you set that up however you want, depending what quantities you want to pull out. And you can do a lot of, this is called post hoc hypotheses. You can test a lot of hypotheses, right? You can test the difference between multiple intercepts. You can test the difference between, let's say you had multiple groups. Is there a difference, significant difference between the slope of group C compared to the average of the slopes of groups A and B? So that W matrix can truly contain any hypotheses that you as a researcher want to design. And you can extract the standard errors and any associated statistics for that weights matrix, depending on what it is. However you want to combine those coefficients to pull out interesting quantities for you and for your reader, depending on what those are, you can compute. You can compute all those things. So very often in like linear modeling statistics, we have like lots of different multiple comparisons between groups. Those are all done using a matrix like W to calculate, at least quickly. You can do it that way. And when you have these things where you have some sort of slope or complicated relationship, you can compute all sorts of like interesting features between those two variables. And you can have quadratic terms. You can have like lots of things in here that you want to model. And then you need to basically you need to take that vector of coefficients that the model spits at you and digest that into summary statistics that make sense that you actually want to interpret, I think, as a researcher. So that change in the slope is an interesting quantity, but I might want to report what the two slopes are, or like how that has changed, things like that. So you need to have these sort of tools to get at to get those quantities of interest. So you can do any sort of hypothesis you want. You can do any linear function is allowed in W. So what are linear functions? That's addition, subtraction, multiplication by a scalar, right? So an average is a multiplication by a scalar because you're multiplying by some normalizer for the whole thing, right? So yeah, anyway, that's that. I think I'm going to end it here because the plot stuff is going to take too long. So we do plots next week. So next week we'll just make graphics. But yeah, cool. So hopefully that was useful for you guys. But yeah, great, cool. OK. Yeah, thanks everybody. So we'll just continue the same code that we're using right now. We'll just continue using that next week, and we'll use that to design all the plots. Because we'll just move to the end and just design all the plots.